Hello, welcome to Quantum Leap. Here we are going to discuss normal helium atom or ground state of helium atom. A helium atom consists of a nucleus, that is Je, at the origin, and two electrons. Uh, this is first electron E1. Okay? The radius of this electron is R1. The second electron radius is E2 because of helium atom consists of two electrons, right? These are the radius. Okay. So distance from the first electron from origin of nucleus is R1 and the second electron from origin of nucleus is to the radius or distance. Here we are going to neglecting the motion of nucleus. Since we are discussing perturbation theory, which means energy correction methods. So because of that, here I'm mentioning specifically the we are neglecting the motion of nucleus. Okay, now we're trying to arrange the Hamiltonian of the system. Okay, the Hamiltonian of the system, the kinetic energy and potential energy, right? And the interaction between the two electrons also. Here we are considering this potential energy also. Okay, so we are all aware of this type of interaction, right? Right. The distance between the two electrons is r1, 2. So here I'm going to try to arrange the Hamiltonian of this normal helium atom. Hamiltonian H equal to the kinetic energy of the first electron and the respective potential energy of the first. This is the first electron kinetic energy and potential, and minus h cross square divided by 2m del 2 square minus that e square divided by r 2. Okay, plus, so because of electron electron interaction we generate some electrostatic potential, that is e square divided by r 1. So where this delta 1 and delta 2 refers to the coordinates of E1 and the E2, I mean electron, first electron, second electron. So the term minus Z square divided by 1, I mean R1, potential energy between the electron 1 and nucleus, and this term is minus Z square divided by R2 is the potential difference between the second electron and the nucleus. Here the important term is this one, E square divided by R12, the electrostatic repulsion between the two electrons. So if you consider the simple case, let us consider one simple case. A Hamiltonian for first electron. We try to write the first electron, the Hamiltonian. So the H Hamiltonian 1 means the first electron Hamiltonian minus H cross square divided by 2m L1 square minus this potential energy of the first electron on the nucleus. For example, for second electron Hamiltonian is Hamiltonian 2 equal to minus H cross square divided by 2m del 2 square minus Z e square divided by r. So now the total Hamiltonian of the system I'm going to write like this. The total Hamiltonian of the system H equal to H1 H2 plus electrostatic potential energy. So this one is very difficult term to calculate the integration term. So remember this one. Okay. So the Schrodinger equation, the corresponding the Hamiltonian 1 and Hamiltonian 2 exactly soluble, and the solutions are the simply the hydrogen wave function. We can use this hydrogen wave function, we can solve easily. So we are already done this thing. This is simple. It is consist of one electron. Then it is we are considering the simple hydrogen atom. We can easily solve using the Schrodinger wave equation. Solve easily type of energy. So I'm going to use simple solution, hydrogen wave function solution. Okay. So this is Schrodinger wave equation. Schrodinger wave equation. The simple solution h cross square divided by 2m L1 square minus Schrodinger equation we know, right? H psi equal to E psi. This is H. Okay. Wave function psi of C. So here I'm taking the ground state for simplification. Okay. This is Schrodinger wave equation. H psi equal to simple. This is our Hamilton. So if you solve this one, this is hydrogen atom, right? So if you try to solve this thing, so easily you can get the answer here. The energy of this one, energy equal to minus z square m e power 4 divided by 2 h cross square. Many times we solve this type of equation. On the ground state wave function, ground state wave z cube divided by pi a naught for radius whole power 1 divided by 2 e minus z, this is important, r1 divided by a naught. This is equation number one. In a similar way, if you try to put the second Hamiltonian, you can solve the similar equation Om delta 2 whole square minus Z E square divided by R2. Okay, this is wave function, the corresponding wave function. E2 of 0, this corresponding energy, and this is the corresponding the wave. You will get the same answer instead of R1. Here you can get R2. Okay, here the A naught is the very very important one. Bohr radius. We already discussed this one. H cross square divided by M e square. Or else you can write this one, the Bohr radius. Okay, radius. The wave function and energy eigenvalues corresponding to the our Hamiltonian is wave function and energy eigenvalue corresponding to Hamiltonian 1 and Hamiltonian 2 are, the wave function must be multiplied, energy must be added, right? The other two wave functions. So it is better to do the equations. Similarly, you can consider here this equation, the psi 2 of 0, okay, that keep divided by you know whole power 1 divided by 2 e power minus z r2 divided. This is equation number 2. Okay, important. This is equation number 3. So if you observe clearly here, the wave function, total wave function of our Hamiltonian in helium atom, ground state of helium atom Hamiltonian, the total eigenvalue of the ground state helium atom E1 plus E2. Energy must be added, right? So E1 we already know that, minus Z square M e power 4 divided by 2 h cross square, and plus, okay, because the plus is there, and here the minus is the minus. So if you try to avoid this mistake, then you can remove this one. Directly you can use here the minus. Okay, then it's fine. Hmm. Minus z square m e power 4 divided by 2 h cross square. So we got this way by solving this simple uh, a, I mean hydrogen atom. Okay, if you try to solve this hydrogen atom solution, then you can get the ground state of energy and the corresponding eigenvalues and eigenfunction of this Hamilton. Okay, this is the energy, important one. If you solve this type of questions, definitely you can easily solve variation method and WKB approximate solution. You can understand easily why we are using the variation method and WKB approximate. So this is just perturbation theory. So if you further simplify this equation, then you can get 2z square, right? The m e power 4 divided by 2h cross square. If you observe clearly here, these are all the constant value. Then I'm going to use one design one letter here, that is minus 2z square wh. Okay, heterogeneous ground state. So we know that the wh is the value. If you try to put this all is constant, well, then you can get 13.6 electron volt. Hence, the H1 plus H2 can be regarded as the unperturbed Hamilton. So this is simple one. That's okay. If you want to find the correct term energy, this is unperturbed term. So our aim is, especially in perturbation theory, the perturbation terms. So right now, up to here only we are calculating that energy and term. This is unperturbed. That means H. Okay. This one is important. This is perturbed. So next step, we are try to solve this unperturbed. Sorry, perturbation term energy. After that, we can add that perturbation energy into perturbator. Then we can calculate the exact ground state energy of this normal helium atom. Okay. So here I'm going to use one board here sentences. Hence, Hamiltonian 1 plus Hamiltonian 2 can be regarded as the unperturbed Hamilton. And is E square divided by R12 term as a perturbed term. Perturbed Hamilton. Okay. So first I'm going to correct this one. First order correction to the ground state energy is first order correction to the ground state energy so E1, I mean first order ground state energy. So integral psi star E square divided by R12 psi theta. This is first order correction energy, right? You are all aware of this thing. Okay, first order correction energy. So this n is the nth state of the corresponding wave function. Here we are using the ground state wave function, right? So if you try to use the ground state wave function, so by using equation number 3, I'm going to this equation number 3 here is the equation of psi multiplied. So I'm going to write this one, the corresponding first order correction energy term like this by using, I'm going to mention this one by using equation number 3. Okay, the E1 first order correction energy double integral psi 1 complex psi 2 complex 0 indicate the ground state of hydrogen atom E square divided by R12 psi 1 of 0 psi 2 of 0 is better to use like this. The volume d tau 1 d tau 2. Okay, now you can use equation number 1 and 2 to these two equations. Equation number 1 and 2. Okay, psi 1 is there, here psi 2 is. So after using this equation number 1 and 2, you will get z cube divided by pi a cube e power s2 z r1 divided by a naught. Okay, then e square divided by r12. Here also same thing, z cube divided by pi a naught cube e power minus 2z r2 divided by a naught tau 1 tau 2. So where is tau 1 equal to r1 square sin theta 1 dr1 d theta 1 d pi 1. Okay. So similarly, d tau 2 equal to r2 square sin theta 2 dr d theta d pi. Okay. Then I'm going to simplify this one like this equation. This very complicated E1 equal to z power 6 e squared divided by pi squared a naught integral 0 to infinity. Okay, because here r is there, 1 divided by r12. The remaining portion, e power portion, I'm going to write like this, e power minus 2z divided by a naught. The only thing r1 plus r2, r1 plus. Okay, so this is the final equation. So we got this one. We try to solve this one. Very difficult solution. This one. So I'm using this one directly answer here. We try to solve this equation. You'll get an answer like this. Okay. First order correction energy 5 divided by 4 z m e power 4 divided by 2 h cross square. So if you observe this one is clearly this WH, right? E power 1, the first order correction energy, 5 divided by 4 Z W in hydrogen at ground state, 13.6 electron volt. Okay. Now it is time to arrange the correction. The energy corrected to the first order is total energy of the Hamilton system unperturbed energy less first order correction energy. So what is unperturbed energy value? We already calculate, right? Minus 2 Z square WH plus what is first order correction energy term? This 5 divided by 4 Z WH. Okay. So E equal to minus, you write like this equation 2 Z square minus 5 divided by 4 Z, okay, W. So this is the final energy term. Final energy term. So if you want to calculate this type of systems, for example, here if you take this ratio first order correction energy term divided by this ground state energy term, but equal to, this is 5 divided by 4 ZWH, right? Divided by ground state energy, this 2 Z square WH. So here by using this term, okay, E1, I mean first order correction, ground state, we try to focus on this one, 5 divided by 8 Z. The correction is subtractive, which is understandable since the effect of the electron-electron interaction is to be reduced. The electron nucleus attraction, the resultant hold good for only two electrons atoms like system. This result is only good for only so electron, two electrons atom. Like for example, if you consider lithium plus lithium plus beryllium plus barium plus plus and so on with that Z value equal to 3, 4, 5. So these are all the corresponding the correct energy term. Okay, this is how you can calculate the first order correction energy terms. So here I'm going to give the quick revision, the ground state of helium atom. Here we did only the first order correction energy term, right? So first here we try to arrange the Hamiltonian of this given system. Then step by step, first I calculate this one and perturbed Hamiltonian system corresponding energy that corresponding wave function. After that, I try to correct this electrostatic potential by using the first order correction energy term. Add the total energy, then I'll find the correct energy of the ground state of helium atom. So by using this type of derivation, we can explain, we can go with the two electron systems like uh, materials also. Okay, these are the few examples.